So the idea with flow, we haven't really formalized flow and not flow. So we know that for all the edges, we're going to have some sort of number or some sort of flow value, right? So we like to assign it. Specifically, how do we assign flow? And we're saying that if we use this forward-focusing algorithm, that we can find this maximum flow value that obeys all our conservation rules and that maximizes the throughput of the network. To talk about it, or to talk about the capability of the network to improve further, we can start to consider something called residual capacity. So residual capacity, we can take it as delta. So it's the ability of the network, given a certain flow configuration, to change. So if we define it for an edge, so let's define residual capacity as this. So given some edge E, it's just the amount of flow that we could assign to it. It's not a super big deal. It's pretty simple. So specifically, if we want to think about what the forward-focusing algorithm will do, or what we'd like to do, is given every path. So if we actually take this path as an argument, and our residual capacity for a path then. Is a little clear, so let's consider for path. So for some arbitrary path, does anybody have an idea if I want to consider how much capacity we have left over in some arbitrary path? Say we consider this path. The current flow amount is 0. What's the residual capacity? How much can we improve? So the current flow is 0. So basically, how much can we push through this pipe? 12. And here it's 4. So that's in these cases, these would be our residual flows for P1 would be equal to this, and for PJ would be equal to that. And so in general, it's going to be equal to the minimum edge in P of this function, just the residual capacity. So that's useful to think about. We already kind of knew it intuitively, but this is where we're going to start to set up just a little bit of notation to talk about these ideas. So specifically, if we consider our network, now we can actually, maybe we can draw a diagram of the picture of how well we can do. So, given so let's take a network and a snapshot of time. So say we've already done some improvements, we've assigned some flow values, and now we're considered with the idea that we might want to try to improve it further. But it's very unclear, as we remember from before when I drew the other diagram, it was very unclear as to whether or not we could even improve the diagram. So now, maybe if we talk about these residual capacities, we can do a bit better. So if we consider some flow at time t, we might have something that looks like this. So same beast again. This time I'm going to draw everything. So in this case, I'm going to write the flow value. So if I'm writing flow, up there I was writing capacities. So it's just good to keep these, like this is what we're putting down. Five, 0, 9, 4, 15, and 8. So this is our current situation, and we'll kind of stick with this sort of situation for a while. And the question is, given this starting point, is there a way that that we can improve the situation? And we have the same node labels on this graph. So this is a bit of a trick question, and I don't want to dissect it, but it turns out that if we just straight away consider optimizing, that we actually, if we just think about adding flow to nodes, it turns out that we can't do it directly, and there's a good reason for that. And that's because if we look at these nodes here, they are already maximized. So we're stuck. We're stuck here. There's nothing we can add. We can't increase anything to push more flow. You know, we have 17 plus 14 here. That's exiting. Everything adds up, and we can't physically put more through the network. And I can tell you that this is actually not the maximum solution. It's maximal. It's maximal because we've reached the point that we can't consider it's a local optimum, but we can't improve it further using a sort of naive finding paths and improving paths approach. And so this is where the forward focus and algorithm starts to consider this idea of residual flows in more detail. You guys don't need this. Let's keep it. Let's keep it.
I don't know if this is useful, but could we generalize that we have a cycle, then at least one of the edges has to have zero flow?
We'll get to ideas like that later, but conceptually right now, I think, what do you mean?
Well, like that triangular cycle there,
Like here?
No, the next one over, the one with a zero.
Oh, yeah.
Because if we divert any flow there, then we're just overloading edges without actually getting...
When we're optimizing in the forward focus and algorithm, we generally consider complete paths. So we'd be optimizing an entire path. So we would either, and in the algorithm so far, I've only discussed the increasing end of things. But there is an end of things where it's possible to do a decrease as well. And that's sort of what we're talking about. So it might be possible to change things so that we could actually, there's actually a concept called backflow, which is the idea that, well, if we loosen up what we're doing, like maybe this edge here doesn't need to be 5, and then that will free up resources here to increase, which might actually change things. But the fact that this is 0 alone isn't necessarily an indicator, because...
No, so I'm not saying that by making that 0 you maximize. I'm just saying if you have a solution and you find that in a cycle you don't have any 0 nodes, could that not be an indication that that's not optimal?
You don't have any 0 nodes. What do you mean by, the residual capacity is 0?
No, like flow, that's flow, right? No.
This is flow, yeah.
Yeah, so that's 0. If it weren't 0, then it means you're draining away from the destination. And like...
Oh, you mean if you're so you're saying the fact that this is like that we're going backwards is an indication that...
Not so much backwards, but it's a cycle. So you're just occupying kind of capacity in those other two nodes if you put anything other than 0 there?
I think there's a more general property that we're gonna see emerge in a second, which is really clear to talk with this. But it might probably maybe tie into the same, I'm not sure exactly the property you're talking about, but it might be connected, perhaps.
Okay.
Yeah. Yeah. I'm not sure, and so when you're talking about, so you're saying that in a triangle there's no way to improve flow? You might not be understanding the,
No, so what I'm saying is if you have a cycle,
okay, so this guy,
yeah, there has to be at least one node, one edge that has 0 flow.
that has 0 flow?
Otherwise, you're going to be using, so say you put a 1 there, then that you're going to have to decrease the 13 because that 4 has to take into account the fact that now there's a 1 coming in.
Yeah, I see what you mean, but I think in general what you'll find, and I don't know if I'm completely correct in saying this, because there's a few proof techniques for this sort of idea, but I don't know if just looking at a subtriangle will tell you, like a subflow like that, will tell you a lot about the complete graph, but it perhaps could, like it seems like you're onto something, but I think it's really easy, it's a lot easier to think of it in terms of paths, and specifically, like really right now, I think the easier way to identify when you're stuck is by looking for something called cuts. And we're going to talk about that in a second. But the idea is that, we have this subset of edges that isolates all the flow in the graph, and there's no way to improve through the whole graph the flow through this like sort of conduit, if you will. And because of this idea, and since it covers the whole network, we're kind of stuck. We can't just increase a number. But we can. But I think you do have a point, because you're saying, there is this idea of introducing backflow, which we can talk about, and that can get the algorithm unstuck. If we think about trying to take steps forward in time towards the optimal. So let's talk about backflow, and let's improve our notation, and we might even hit upon your point a little more clearly and have better tools to talk about it. So the idea of backflow is that we can allow so the idea is that sometimes, taking a little step backwards helps. To visualize, we have to generate an idea of a residual network. NF. So the general idea is that this NF, I'll show you here. This is F at some T. So we're going to include in this residual network the current flow. And we're going to define our residual network based on some flow amount. I'm adding a T index. You don't have to. It can just be some arbitrary flow. But I like to think of things in terms of the algorithm improving over time. But then I also drop the index sometimes. But the general idea is that for all U's and V's, so for all the edges that have So we want to have an edge for all these conditions, and an edge in this network. And I'll draw an example in a second. So every edge that has some latent capacity or some residual capacity, we want it in our residual network. So we just want to generate a picture in another network of sort of options we have. And then we also want to track all the, yeah. We want to see if there exists a residual capacity So basically all this is saying is just that for each edge with residual capacity, we're saying that we're going to put like a CF value into a residual network. So I'll write it in English as well. Because math is in English. So for each flow value, keep a representation so we're just going to keep track of these residual amounts. Yeah. So let's see here. So what's the best way to draw this? So in the residual network, we're going to have backwards flows and forwards flows, and sometimes people draw them on the same graph, but it can get really hairy. So we're going to do something a little bit different, just to really clarify these concepts. So let's just draw a diagram of a residual network for that flow. I'm going to break it into two subnetworks to really make the backwards and forward flow components really clear. So the first one is all of the forward flow delta values. So we have these delta values. And then down here we're going to have our backward flows. But the total network will be both of these together, or both of these in unison. Like they're both part of the consideration. So if we draw the nodes, let's consider this guy's 8. This guy's 9. So these are the unused flows. So if you notice over there that we're missing 8 from the first node, and we're missing 9 backflow here. And so these are just unused, these are untapped potential, if you will. And so I can sort of see what you're talking about with the triangle emerging earlier. Do you know what I mean? Where, you know, there's definitely a triangle here, but then here we have a broken link. Like there's nowhere, if we consider the residual flow that we can add directly with our deltas in our NF, we can't, we can't go anywhere. But we know that wherever we've assigned flow, there's also a backflow value we can consider too. And so this is the crux of the deal. And so in this sort of like backflow network, I believe this was, is this 5, 7, then we have 2 then. Maybe it's a 2. So here we see that this is our capacity to reverse the direction we've already gone in, right? And so this is sort of the network. If we formed a network of reversing our direction, this is what we would have. These would be the edges. So this is sort of the back network and the forward network we can consider, right? So we can consider our residual capacities and this like sort of residual network, and we can make some decisions with it. And I'm drawing it like this so that we can really see the juxtaposition between both of them, because you can almost see through these two networks together a decision that we might be able to make. Does anybody see it? So that's our unused forward capacity, and this is our back capacity. It's how much we can go backwards and how much we can go forward. And our CFs are just equal to the amount of capacity we have unused. Or should be. Yeah. So if we consider, does that make sense? I feel as though these should actually, maybe I should put down the values. I have to double check these numbers. But the general idea continues. Let me see here. All right. Okay. So the general idea, however, is we want to augment. And the way we want to augment is we want to add our unused capacities to our what do you call it? To our through our forward edges. And our backflow capacity. For example, our backflow capacity of this node is 4, because our flow is 4, and the capacity is 4. So we can actually backflow as much as 4. And I'm hoping that they all work out like that. So that one's 4, that's 4, that's 4. That one's 17 and it's maxed out, which we can, so since that one's 17, we can backflow as much as 17. So I think things are working out. So, yeah, so then given these two nodes, or these two networks, we can sort of spot an augmenting path. If we consider this idea that maybe if we move, from here to here, then it also looks like, if we look on this graph, then, well, given all the backflow capacities, we can then move from here down to here. So then we're at this node, and then over here, we can go from here to here to here to here, right? And that's a path. So that gives that is one backflow edge. And 1, 2, 3, 4 forward flow edges. And that's unused, that's like latent capacity that we haven't used in our graph. Does that sort of make sense? I separated it into the back and the forward so we could really, and put them on top of each other so we could really see this idea emerge. This idea that given our graph, we can analyze it from two perspectives at the same time, which is what's our unused forward capacity. If we only look at the forward capacity, it's very clear that there's no way to push more through this sort of gap. But if we also include our backwards capacities, then we realize that without violating any conservation rules, we can actually find a new flow. And it turns out that it's this one. And I'll do this with the dotted line. Okay? So that's what we'd actually put together by comparing our residual forward and back flow capacities. Does anybody want to tell me what the delta of this path would be? Like if this is P? It's nothing crazy. It's just like every other path we've looked at. But how much can we improve the graph given this path? 2, yeah. And so I don't know exactly what the triangle thing you're talking about is, but I feel like you do have a point with the triangle, and I think we can see it emerging. But I don't think it's a property of the whole graph. I think it's because you can see that there's like local properties that limit.
Yeah, no, I was thinking more of it as a spot check. Like if you're doing it by
Yeah.
hand, it's like, oh, it can't be right because of this.
Yeah. I think you could probably, in general with these networks, you could probably find many spot checks that can tell you when you're wrong, but not a lot of spot checks that can tell you when you're right. And that's the case. So yeah, I won't construct the network. Well, actually, maybe I will. Do you guys know how you would take this path, the fact that we're pushing through this network, and augment the original network? We can do it together. So what we'll do is we'll just go along that path and we'll increase by 2. So the flow here, so we'll change to t plus 1. This will go up by 2. This 4 will go down by 2 because we're pushing backflow through here. So really the idea of backflow is just that we've modeled the forward flow and we've taken it into account. And now we're just subtracting 2 from it. And before we were blocked here, we couldn't do anything. But now we're not blocked because we're considering the idea that, we can take a step back. And the step back for this node preserves the conservation here. So if we push 2 in, then we can actually just not take 2 extra into this node and still preserve conservation. And that carries through all the nodes, right? Because then now there's 2 extra here. So this has to go up to 11. And then this has to go up to 7, which we can do. And this can go up to 19. And without violating any conservation rules, we've been able to apply information from the residual networks, both the missing forward flow and the back flow.
So there's the top node that you circle, so 2 and 2 is 4 and there's 12 coming out.
Oh, yeah. Oh, sorry, this is 10. Sorry, yeah. 10, 12, yeah, sorry. Thank you. You guys are really good today. Awesome. I don't know what my problem is. I think it's all the vertices and lines in this and these examples. It's really easy to write a wrong number. Conceptually though, is it cool? Like, I think it's interesting that we can get stuck trying to do a greedy optimization by increasing flow, and then suddenly you can pause and then consider the capability that the network has to take a step back, and then combine that with your potential to go forward and see and use those 2 networks to find a path. And so when we look up, like if you look up residual networks in the textbook, they explain the idea not as intuitively as this. I like to separate the idea of the back flow and the front flow and really picture it. See, like this is the forward bit, this is the backward bit.
Can you explain how you got the 2 from the augmented?
Yeah, this 2, it is...
The final 2?
Oh, the final 2?
Delta FB equals 2.
Given this path, there's no way I can put more than 2 through here. Does that make sense?
Alright. Oh, because the 2 is the minimum.
It's the minimum, yeah, it's just the minimum on the path, yeah. Yeah.
Okay.
So that's really the algorithm. Like the algorithm is not too crazy. There's always so many cool things to talk about so little time. So, I mean, what do we consider after we talk about every algorithm? So this is what the algorithm does. I'm not going to go through the pseudocode for it. We can talk broadly about, yeah. Does it make sense though that every step you form these residual graphs? So you have some sort of flow, F0, and each point you construct a residual graph and you search through it for a way to augment your flow. So you search your forward options and your backward options. You just keep taking options to improve your network until eventually you can't anymore. And the situation where you can't is when you run out of a path, considering both those residual, considering your residual network, that can help you complete your journey. There's no more augmenting paths. So the question is does that situation describe an optimal graph? If you just keep greedily improving the paths on your network, does that actually work? And so, I mean, what do you guys think? Probably works because I'm presenting it as such, but.
Well, you end up considering like every single augmented path, right?
Yeah, well,
Exhaust that.
yeah.
So then, yeah, it probably works.
Well, that's the thing, is that, so it seems like it would work, but there's still the same concern that you might end up in a situation where you've settled on a locally optimal solution. And so we need to put some analysis into the idea that it's not actually a locally optimal solution and that we have indeed found the minimum flow, or the maximum flow. Or, yeah, the minimum or best solution. So, okay. Does anybody have any idea of how we might analyze our network to at least verify if something's optimal? And I sort of did it really quickly earlier, and then I dropped it. But it's a general technique that you can use to analyze these flow networks. Turns out that when we were onto something, when I said, given this subset of nodes, there was no way to push more flow through, it turns out that is not too far off a good analysis technique. It turns out that as you do these cuts along the network, that there are some properties that are maintained. So let's define this idea of a cut, first of all. So let's start to consider correctness. So there's a sort of a formal definition, but in English, a cut is a partition of a graph into two subgraphs. They're usually called VS and VT. Does it make sense why they're called VS and VT? The VS is the one that has the starting node or nodes, and the T is the one that has the ending nodes. So we're going to consider cuts that separate S and T exclusively. And it's going to have this property such that if we take the union of them, that will recover the original vertices. So we know that, for example, that the union is preserved, and we're also just going to say that, if we take the intersection, there's nothing there. So it's all the nodes and no redundancy. In general, as the subscripts might suggest, all the S's or AS is in V, and the S and the T's are in VT. I wonder, do I still use this example? I think we do. I keep finding myself wanting to kill that, but I think it's useful to have it up. So we use it on the law. So, given a really ugly So, yeah, so the general idea is, like, in a conceptual sense, is you have all these graphs, they have some links between them. I'm not going to draw them all. You know, this is a VS. And what's important that we're going to have to consider with the VS and VT, because when we did the cut before, we found that we couldn't push any more flow across it. But when we're doing this, we want to broadly consider, you know, a forward node or forward. Maybe another forward. I don't know why the network's structured in such a way that from way back there, maybe a better link would be here. Whatever. And you might have a backward one too. And this is a cut. So every cut is going to intersect with, like, long as you have some nodes on either side and your graph is, you know, all the vertices are connected, you're gonna get something with every cut. Yeah. And so what we're really interested in when we're doing these cuts is we're really interested in these guys. We're interested in, if we call these, you know, the sources and the destinations, we're interested in the nodes that go forward and backward. And so if we want to formalize that just a little bit, we just want to say that our forward nodes are all the UVs, such that U is in VS and V is in, little v is in VT, and all the back nodes. How do we set that? Yeah, okay. So we're going to keep the general convention that for the arrow, the U is the source. We've done that so far, and we're going to keep on with that. So the U is in VT, and the V is in VS. So, yeah, so all these arrows with their, this would be U, T, U, T, U. Or, well, I shouldn't say U, I should say E, sorry. Yeah. And so, and we're not really concerned when we do these cuts. The reason I drew these as clouds is because we're really not concerned with the interior structure of those graphs. We're really focused only on these edges, and everything else is kind of unimportant to us when we do these cuts. And furthermore, when we consider these cuts, is there anything you think we can say about these cuts? Like, I mean, already given this definition of a cut, this is no longer such a bad situation. Like the situation where we ran out of, where we couldn't optimize any longer, no longer seems that way with this cut because we have a backward edge. Yeah. So, how are we doing for time? 7 minutes? Okay, great. Yeah, perfect. So we have just enough time to really go over the definition of a cut. So for any cut, we have a forward and backward set. Let's define some sort of X as a set of vertices that are cut forward in the cut, or that it's a set of vertices that are in VS and VT. This notation is pretty loose. It's used in the book too. It's weird, but it's such that given this set of cut vertices or cut edges, so it's all the nodes that start in VS and end in VT, right? So it's all these. We can call this a set of spanning edges. Yeah, such that they span the gap from VS to VT. And we want to define this capacity of X as just the sum of all the capacities of all those edges of the cut, where the E is in X. And I really want to say that this is the forward capacity. So each cut will have a unique forward capacity if we look at the edges and we sum up the capacities of those edges. It's also going to have a forward flow. So let's set these forward as well. So let's set our FE is our flow over the cut. And this is our capacity over the cut. So given these flows and these capacities, we can get some work done. We also have to consider one more thing. Does anybody know what that is off the top of their head? We consider a forward flow and our forward capacities. I actually forgot it in my notation too, so that's pretty neat. Our flow over our cut isn't just going to be the flow forward. The flow over the cut is actually, sorry to destroy you guys. It's going to be, and I'm going to crunch this a little bit. I was going to leave it as a cliffhanger and then do it with another chalkboard though. It's easier to do it this way. So this is our edges that are backwards. X backward. So our total forward capacity and our total flow is going to be equal to whatever we're doing forward minus, in this case, the one backwards edge. So that's actually an expression of our total effective flow, if you will, over a cut. That's how much work is getting done by this cut. Yeah. So if we take this definition over to this cut over here, we should have, what is it? You know, our capacity of this cut here is equal to 25, and our flow is equal to 25 minus 2 for the backflow. I think that's right. Yeah. Yeah. Oh, the numbers are working out. That's great. Yeah. And so it's a useful tool for analyzing these networks. What are we doing? I just feel like we're going to really get proofy in about 5 minutes, and I don't know. Let's see if we can isolate this into little packages and talk about them. Okay, so what can we say about cuts? So I'm going to use up your last 5 minutes, so I'm going to talk a little bit about cuts. Does anybody have any ideas? Give it a cut. I know you're.
For any cut, the flow is the same.
Any cut is the same? Yeah, so as we're going through the network, you can definitely, and I think that's a result we'll definitely get to. And that's what we feel like, is that the maximum flow through the network is going to be constrained by our cuts. It's going to be constrained specifically by our minimum cut. So the maximum flow we could ever push through the network is going to be described by some sort of limiting point somewhere. In terms of proving that the algorithm works, we have to start a little bit from the basics, and I guess I'll just do it right here. And we'll just put down the first sort of candidate lemma. So really, it's that for any cut over x. For any capacity x over a cut, and flow, we really want to assert that, you know, our flow of x is less than or equal to our capacity of x. So this is the first thing that we just want to make sure that if, given the backflow definition and given everything we've said, is this still true? is it true that given the capacity over a cut and or flow over a cut, that this sort of, at least this equality is maintained? And, you know, this actually decomposes. Like we know that this f of x, or the x of this cut, is equal to the sum of the forward flow. I'll just write forward, minus the sum of the backward flow. Oops. My brain knows there's only like 1 minute left and it's trying to go really fast, but chalk can only go so fast. Yeah, well, we can just take this expression, so let's just draw a line. We can take this expression to be our forward sum. Right? So given all our forward edges, we can just say that this f of x is less than or equal to this. And then we also know, just by definition, that I kind of ran out of space, but I'll just do it. Maybe I'll finally erase this guy. At least the top. Oh no. Slightly better. I don't know if it's visible up there or not. But it's really simple. The general idea is that, you know, given, I'll just, so it's less than or equal to our forward sum, and this, you know, we also know that this has to be less than or equal to our capacities. Like we know that the flow in our network although I'm running it out in so much detail, but and this is the first step. So we know this is true, just by we know this definition is true. So then that leads naturally to, and this is the definition of C of x. So that just leads naturally to ooh, and this should be an E. Anyway, I jumped ahead, jumped again. And I think that actually did it to the minute. Does that make sense though, if we make a cut and we, you know, if we want to prove that over a cut we can't exceed our capacity, that we clearly can't, because the maximum we ever have is our forward flow and no back flow. And in the case that we take a sum over all our forward flow, then that is the definition of our capacities. So we can never exceed it. It's good? Okay, good. I saw people like, oh.